Okay, so we were looking at directing groups on Friday. And now we're going to look at how we go about deciding where our most likely new electrophilic aromatic substitution is going to occur. So if we look at this example, first off, our substituent is this. Is this a electron donating group or electron withdrawing group? This is an electron donating group. That nitrogen does have a lone pair. Remember, if it doesn't have a formal charge, this is why it's so important to represent your formal charges. So it is an electron donating group. So it's also going to be activating based on the fact that it is an electron donating group. So it's going to mostly add orthopara, but because this is a big group, we're likely going to be our major product is going to be para based on sterics. So whatever we are reacting it with, that's where it's going to be directed. Now what if we have multiple functional groups that are already on the ring? Well, what we want to look at is the directing ability of both of those functional groups. And remember, the terms ortho, meta, and para are based on whatever functional group we are talking about. So those positions can change relative to whatever functional group we're discussing. So let's start with the CH3 group. This is a weak activator, and it's going to be ortho-para directing. So that's with the pointing. Now notice the para position is typically going to be major based on sterics, but the para position is already taken up. And remember, we cannot have the electrophilic aromatic substitution occur if we don't have a hydrogen, because we need that hydrogen for that last step to reform the double bond. So we don't have a hydrogen in this position, so this position is blocked. It can't direct there. So in the case of our CH3, it's just directing in the ortho positions. Now NO2, that is a very strong electron withdrawing group. And therefore a strong deactivator. Remember, this is going through a carbocation intermediate, so electron withdrawing groups make that less stable. So it's going to be meta-directing. So that's in purple. Now in this case, both functional groups are pointing to the same position. So that's pretty easy. Our position is going to be one of the ortho positions. Now, remember, if we added here or here, that's the same compound. So you don't have to draw it twice. Both ortho positions are available, but that leads to the same compound. So they both point to that position. Now, typically, our electron activators are going to direct easier than our deactivators, because again, this is all about what's going to be the lowest energy transition state. But in this case, they both point to the same position. Now if we look at here, we have a CH3 group, that's a weak activator, so it's ortho-para directing. And again, here's in green. And again, the para position is blocked in this case. We don't have a hydrogen. So the only possibility is the ortho positions relative to the CH3. Now if we look at the OH, that oxygen does have a lone pair, so that is also an activator, but a strong activator. So again, relative to our OH, in purple, we have a different ortho position. And again, the para position is blocked. In this case, we don't have a hydrogen. So in this case, our CH3 and our OH don't point to the same position. So the question is, which one's going to win? Well, which one's going to have the lowest activation energy? And that's going to be the carbocation that's the most stable. And the carbocation that's going to be the most stable is going to be the carbocation that's ortho to our strong activating group. So the stronger the activator, the more likely it's going to be to direct. So it's more powerful, it's going to dominate. Activators are going to dominate over deactivators, because deactivators increase the activation energy. So the stronger our activator, the more likely it is to direct in that position. Does that mean we won't have any in this position? Well, it depends on how strong the activator is. This one's a pretty strong activator, so it's really likely that all of our product is going to be ortho to the stronger activator. Now let's look at this case. What we have here is both weak activators, and they're both going to be ortho-para directors. So based on the CH3 group, green is in pointing. Again, in this case, the para is blocked. And purple is based on the isopropyl group. Now, there's really no difference in strength of activation between our CH3 and our isopropyl group. So the question is, what's going to be our products? Well, we're going to get both, directing based on ortho of both of those. Now, because of sterics, it's likely that we'll get a bit more of this one, because our functional group is further away from the bigger group. But the amount major probably wouldn't be much. We'd still get a decent amount of that. So they have the same strength and activation. They're both going to direct. And sterics is really going to control what's going to be our major product in this case. Now if we look at this case, again, both of these are the same strength. They're both weak activators, so they're both ortho-para directors. But we only ever get these two products and not this product, even though we would direct to this position, and that's because there's just too much sterics between them. So when we have a group and a group here, it's likely based on sterics that it would be hard to get this position if we have other available positions available. Because again, there's just a lot of sterics there. Because they're so close together, they are meta to each other. But that position is being directed to. It's just because of sterics that it's unlikely to be observed. And of course, our most major would probably be this one based just on the sterics considerations. Because again, directing ability is no different between those two. Bless you. So if we're looking at this one, NO2 is an electron withdrawing group, so it's going to be meta-directing. So that'll be B. That's our only functional group there. And again, we're adding Cl2, AlCl3, so we are adding chlorine. So these are wrong because that's CH3. That's not what these reagents want. There's no carbons here, so there can't be any extra carbons in our final product. So that is a chlorination. Now if we look at this one, we have a electron donating group, and it's strong. So it's a strong activator because we have lone pairs. So that one's going to be ortho directing. It's also para directing, but the para position is blocked, so I'm not even going to point towards it. And then we have our SO3H. That is an electron withdrawing group. So that's going to be meta directing. So meta to our SO3H is that position. So our answer is going to be the bromine, ortho to our oxygen, and meta to our SO3H. So that would be A. Oops, why did it go so fast? Remember, we are not getting a replacement of any of our groups. We have to have a hydrogen in our position for it to direct it. So this is our what we do. And again, if they did direct in different positions, our strong electron donating group would win for directing anyway. So really, it only matters about our OH. Now, what if we wanted to get the bromine in this position? Would this be, if we just added BR2 and FeBr3, our major product? So let's say we just took this starting material and we added FeBr3 and Br2. Would we get this as our major product? You're shaking your head no. Why? So if we did this, our major product would be in the para position because of sterics. We'd get some of this, but not enough for it to be useful in synthesis. So we'd have to separate it out. We might get a small percent yield. But we want a big percent yield in synthesis, the biggest possible. So if we wanted the ortho position, and we have a big group like this, it's really unlikely to work. So this isn't the best route, and I will mark it wrong if you just put FeBr3 and Br2, because that would give you para as major because of sterics. But what if this is what we want as our major product? Well, we can do that, and we can exploit a reaction that we did discuss already in the fact that we are ortho-para directing, mostly para because of sterics. So what if we put something in the para position first and then react and then remove it? So we can do that. We can have a para position to block that, because remember, once we don't have a hydrogen in that position, we can't get the reaction to occur there. So let's say we put a blocking group. Now we don't have a hydrogen here. So now when we react, then our ortho position is going to dominate here, and then we can remove the blocking group. So to do this, we need a group that will react and add to the para position. But the key is it needs to be easily removed because it's not in the final product. But we did talk about a reagent that's easy to remove and reversible, and that was reacting to form our SO3H. Again, that's not going to be a very useful group to have for any other reason other than the fact that it's easy to remove. So we're going to use that as a blocking group. There will be limitations, however, and we'll talk about that. So there's not a lot of reasons to have this as our final product. There might be some, but for most cases it is not. So its main use is that it's really reversible. It's easy to remove. All the other reactions we talked about are not easy to remove, but this one is. So if we reacted with our concentrated fuming H2SO4, remember fuming is our gas. It's not just H2SO4, there's more there. And then we can remove it after the reaction. So if we take this group and we do the fuming H2SO4, then we will block that para position. Now our SO3H is electron withdrawn. So it is beta directing, but that's fine because this is electron donating and it wins, plus they both point to these positions. So we can add our Br2 and FeBr3, and then we can use dilute H2SO4 to remove it, and now we have predominantly our ortho product. And this is the only way to predominantly get our ortho product if this is anything bigger than CH3, because sterics will have major being para. Now there are some limitations to this, and the biggest limitation is SO3H is an electron withdrawing group, so that means acylation and alkylation can't occur once this is on. So this can't really work if we're trying to do acylation or alkylation, because of the fact that this makes our ring too electron withdrawing and too destable to react, unless if this is a really strong activator group. But if it's just an R group, it's going to be too electron withdrawing for acylation or alkylation to occur in most cases. So that's our main limitation, but otherwise this works really well because of the reversibility of this group. So let's look at an example and come up with a synthesis. Now when we're doing a synthesis for these, this one already has two groups on it, so this synthesis is pretty clear. But I can start with benzene, and you can have different electrophilic aromatic substitutions in different positions. But you're going to have to consider directing. So the order is going to make a difference when we're talking about these. Because if you want it in a certain position, but the substituent that was there doesn't direct to that position, that won't work. Just because you drew it on the page doesn't mean the actual chemical reaction will work that way. So you have to follow the directing ability. So in this case, we are adding bromine, but the bromine is ortho to our very strong electron donating group, which is our OR group. So that's going to be ortho para directing, but we would expect to get more para because of sterics. Now this is electron withdrawing, but it's also a meta director. So though it's not going to affect directing as much, it's still going to affect directing a bit. So that means that both of these are pointing to this position. So if we just added Br2 and FeBr3, it would likely be that we would get this bromine, but that's not what we want. So this is another case where we can use that blocking group. So to use the blocking group, we can use our fuming H2SO4. That will put our SO3H in the para position of our ether. Then we can react with Br2, FeBr3. Now everything's directing here. Well, this isn't really directing here, but that's okay, because the meta position is blocked. And then we can use our dilute H2SO4, and now we have our final product. Now you have to remember to do that last step to remove the SO3H. So now we're going to start talking about some of these reactions. So we need a very strong electrophiles for these reactions to work. Because remember, our ring is acting as a nucleophile, but it doesn't want to give up its electrons because that breaks the aromaticity. So we've talked about these reactions, and the reaction I just asked you about on the iClicker was adding an NH2 group, and none of these will add a amine, because an amine is not going to be very not very electrophilic. So what can we do to do those reactions? Well, once we do these first reactions, a couple of these have further reactions we can do between other reagents. One is that with iron or zinc and HCl, we can take our NO2 and reduce it to the NH2. There's no way to get to the NH2 straight off, but we can reduce it. We can also take our CH3, and with excess NBS, we can actually add 3 bromines to it. That's not really going to be relevant for too much, but we'll look at that a little bit more. We can also, if we have a hydrogen in this position, do an oxidation to form a carboxylic acid. We looked at that in chapter 18. So we can do that as long as we have 1 hydrogen in that position. So that's a different group. That makes our benzaldehyde. Also, we can do the acylation and reduce this with much harsher conditions than what this was. So zinc, mercury, HCl, and D. Now note, if we're using these conditions on a ring that have an NO2 and an acyl group, we're just going to reduce the NH2. But if we're using these conditions on a ring that have an NO2 and an acyl group, we're going to reduce both. If it's strong enough to reduce this, it's going to be strong enough to reduce that. So these are weaker conditions and are not strong enough to reduce this. But with the mercury and heat, we can reduce both of them. There's no way to selectively reduce the acyl and not touch the NO2, because the NO2 is more reactive and easier to reduce. So when we're looking at strength of reagents, we have to, well, I'm not going to say there's no way, but based on the reagents that we've learned and the reactions that we've learned, there's always protecting groups we can consider. But right now, that's not what we're looking at. Now, one thing to notice when we do these is that does change the directing ability of these compounds. So the order that we do these in, if we're adding multiple functional groups, can make a difference whether we're going to reduce first or transform first. In this case, we're oxidizing. So we're going to look at that. So for this one, the only way to do this reaction is to do the nitration first and then reduce with zinc and HCl. So this would be B. So when we are putting these together, our order is going to be really important. And we're substituting these, starting with benzene. We have to consider our routes. Now sometimes multiple routes might work, but sometimes only one order is going to work. So we need to consider our directing ability. And also our activation or deactivation. Because remember, we do have limitations with acylation and alkylation in that they can't happen if we already have a strong or moderate electron withdrawing group on the ring. So in those cases, we have to consider that. So first, if we add bromine first, it's going to be an orthopara director. And notice that the nitro group is not orthopara to the bromine. So in this case, we can't do bromination first because that wouldn't direct to the position that we need. That wouldn't be the same compound. So if we do want the correct compound, what we can do is add NO2 first. NO2 is a meta-director, and there's no limitations to where bromine can't react after NO2 is on the ring. So that would be our correct order. In this case, the only order would be the nitration first, followed by PR2 and AL PR3, based on the directing group ability of NO2. So in this case, this is the only route. But there are some times that there are multiple routes. So when you're looking at a synthesis like this, you do have to consider order of putting on these functional groups. So let's look at this example. When we look at this case, we have NH2, and remember there's no way to directly add NH2. We're going to have to go through nitration, then reduction, and chlorine. So the question is, if we add NH2, NH2 is an orthopara director, so chlorine is not in the orthopara position. Chlorine is an orthopara director, and this is pointing ortho to chlorine and para to chlorine. Notice NH2 is not in that case. So does that mean there's no way to make this? There is a way to make this particular one, even though neither of these groups allow for substitution in the correct position. And it's based on the fact that we have to do nitration and a reduction. So one of the groups is converted in its final form. Let's look at those. NO2 is electron withdrawing, and it's a meta-director. But once we reduce it, it's orthopara directing. And it is going to be a stronger activator. So when you're looking at your order and you have to do a reduction, you have to consider, am I reducing first or after? And it depends on the directing and also what groups are present. Because remember, we can't do an acylation with NO2 group because it's electron withdrawing. We can do an acylation with NH2 group easily, but not with NO2 group. Another example of that, if we are reducing our carbon-oxygen double bond to an R group, that goes from a meta-director to an orthopara director. So depending on where our position of our other groups are, we might do the reduction before we add the other groups, or we might do it after. If we look at CH3 and we oxidize that position, that's a meta-director. But we started out as an orthopara director. So again, the order could make a difference. And then the last one, but this one we won't really use as much. But if we brominate the CH3 position, that makes it more of a meta-director because it's electron withdrawing. So this shows 3 brominations, but if we even just brominate it once, that still makes it more of a meta-director. So whether we're going to do that before or after can make a difference in our directing. So we have to consider that when we're looking at the reactions. So for the one we were just looking at, we did the NO2 reduction. So if we do the HNO3, H2SO4 first, and we do our nitration, that's going to be a meta-director, and that does direct the chlorine in the right position. Once the chlorine's there, then we can reduce, and we do get our desired product. If we reduce first, we won't ever get our chlorine in the correct position. If we add the chlorine first, chlorine's already orthopara, so that won't direct NO2 in the correct position. So we have to consider our order when we're doing these. And there is an incorrect order for a lot of these. Also, there's limitations we have to remember. One limitation, nitration can't really be performed on a ring that contains an NH2 group. The reasons for that is you just get a big mess because under those conditions, the NH2 group reacts, and then you're going to get a big mess of some NH2 being oxidized, and it's just a mess. So the reagents of nitration can oxidize the amino group. So if you have an NH2 group already, you don't want to do a nitration because then you're just going to get a mess and you're not going to necessarily get the product you want to get. Those conditions are really harsh. Also, we've talked about this. Friedel-Crafts, either alkylation or acylation, are too slow to be practical when there's deactivating groups present. So anything other than our halogens, we can't really do before we do an acylation or alkylation. So any moderate or strong deactivators, NO2, SO3H, that's going to deactivate enough to where we won't get a reaction. The only electron withdrawing groups we can have on that ring are halogens because they can donate through resonance. Otherwise, we can only do acylations on unsubstituted benzene or benzene that has electron donating groups already present. So when you're considering your order, you cannot do acylation or alkylation if you have an electron withdrawing group already present on the ring. So typically, acylation or alkylation are going to have to be done first, or you're going to have to already have reduced NO2 to NH2 if that's something you're looking at. So you have to keep that in mind. Because otherwise we won't get any reaction. So let's look at a synthesis. So here, we're doing a series of electrophilic aromatic substitution groups, and we're trying to get the answers that we're looking for. So first off, we have to identify, and what I like to do for these is identify all separate reactions I'm going to eventually do, then put them in order based on direction. So to put on the NH2 group, we are going to react with HNO3, H2SO4, and then we're going to reduce it. Now to put on the carbon-containing group, note that this carbon is primary, so the only way to get a good yield of that one is to do acylation followed by reduction. Because if we try to do alkylation, we're going to get the rearrangement based on the carbocation rearrangement. So we're doing our acylation followed by our reduction. Now again, if we have a ring that has both of these on here, and we want to reduce both of them, we just use the stronger conditions. So we don't have to necessarily do two steps. As long as we're using the stronger conditions, we'll reduce both. The weaker conditions will only reduce our NO2. There's no way to selectively reduce this and not touch that because the conditions are strong enough for this one. So the question is, what order should we do these in? So to consider that, now we have to look at our directing ability. So H in our NH2 group is ortho-para, but that R group is meta. So that means that we're going to be adding one of the groups because they're meta to each other while we have that electron withdrawing group present. So notice our NH2 is meta to our R group is meta to our NH2. And both of those, in their form that they are now, are ortho-para directing. So we're going to be doing the reduction after we add the second group. Therefore, we get the meta directing. So here are our two routes. We could add the NO2 group first, and then the acylation, or we can add the acylation and then the NO2, and then we can do the reduction. Well, we do have a limitation for our two routes. We could do our one route, we add our nitration, it's going to be meta-directing. Then we could do our acylation followed by our reduction. Route 2 would be our acylation first. This is also going to be meta-directing. We can add our NO2 and then reduce both groups. However, in this case, only one route is going to work because route 1 is violating one of our limitations. So nitration is not being performed on a ring that already has an amino group. We're good there. But Friedel-Crafts reactions cannot be performed on a ring that has moderately or strongly deactivated. So our NO2 is a strong deactivator. This reaction will not occur. So route 1 won't work because no reaction is going to occur once we have that NO2 group on there. So in this case, our only route is route 2. And this route will work. And of course, we're just going to have to use the conditions strong enough to reduce both of those. So we'll do our acylation, followed by our nitration, that's going to put it in the meta position, followed by the stronger, so we can reduce both to our acyl group and our NH2 group. reaction. So here we have two carboxylic acids. Now the only way we've talked about forming a carboxylic acid was to, actually I don't like this one. I'm not going to put that in. The only way we talked about forming the carboxylic acid was to put an alkyl group. And as long as we have one hydrogen, then we can do our oxidation. So we can do this first step. We can do either an acylation or an alkylation. And in this cat's time, we can actually do an alkylation because of the Lewis acid is allowing the primary carbocation to form. It might be a little slow though. We can also do the acylation. But if we use CH3, we don't have to worry about a rearrangement. But it really doesn't matter what this R group is, because we're going to get the carboxylic acid as long as we have a hydrogen. So you can put 50 carbons on there as long as you have the hydrogen in that position. So it's kind of irrelevant on what that is. But since we want both R groups to be ortho to each other, we might want to use a smaller CH3 group so it's easier to get that ortho position. So if we use an excess of our alkylation, we can actually get mostly the ortho, but this will only work with CH3 group because anything bigger with CH3 would predominantly put para. So if you use an ethyl here, you'd have to do the blocking to get that ortho position. But because CH3 is small, we'll typically predominantly get the ortho just because statistically there's two ortho positions. Anything bigger than CH3 won't get this. Now remember, we said that it's hard sometimes to stop at one acylation, alkylation, and the reason why is this is electron donating. So once we put one on here, it makes the ring more reactive. So if we use excess, we actually can get this. If we have ethyl though, we'd likely get this position and this position. So in this case, we'd have to use CH3. Now you can control your conditions, put the ethyl, use a blocking group, and then put the ethyl in the ortho position. Again, it doesn't really matter what this R group is, as long as there's one hydrogen on each of these carbons. Then you can oxidize to get this final product. So depending on which R groups you decide to use, depends on how this actual synthesis will work. So this is the quickest synthesis. Now this synthesis, maybe using a blocking group might be a good position to take, just because we will get some amount of para products. Because we just will. We'll get some amount of it, probably about 30%. So you would have to separate that. Let's look at one more example. So this is going to be our last example we're going to look at. So here we have our NO2, our C double bond O, and a bromine. So we're adding actually 3 groups now. We have to really consider our directing abilities. Also notice we're adding a carbon-oxygen double bond that's an acylation, so we know we won't be adding the NO2 group before we do that. That's already something you should recognize because, again, we cannot do acylation if we are doing the nitration. Nitration has to be done after. So the last group is going to be the nitration, just because of the fact that acylation can occur once nitration is done. And also, this is saying we're starting from benzene, so that's really key that we're actually adding all 3 of those groups. So NO2 is meta-directing, and also we can't do acylation once NO2 group's on there. So it's a little bit easier to look at just adding this one, since we know NO2 is going to be less. This arrow from reading chapter 12 that we don't really cover is what we call a retrosynthesis arrow. It just means that this forms this. It's a way that sometimes chemists will map out a synthesis backwards. I never really worked well with retrosynthesis. I don't think backwards really well. So that's up to you if that's a route that you want to take. I don't like fully I like showing different methods of solving synthesis problems, but to tell you what's the best route, everyone solves a puzzle different. I wouldn't sit here and tell you, no, it's not okay to solve a puzzle by doing the outline of the puzzle first, because I like to start in the middle and work out, because everyone does that differently. But that's what that line means. It means retrosynthesis, the chemist is thinking backwards. So if we had our BR2 first, then that is going to be orthopara-directed, and then we can add our acylation. Now we can't do acylation first, because acylation is meta-directed. So if we do our acylation first, our bromine won't add in the correct position. Now this isn't blocking any of our problems. We are not doing acylation with a moderate or strong electron withdrawing group present. Will this reaction be slow? It may be, because bromine is electron withdrawing, but our brominations and chlorinations can be done first. It might be slow though. Might have to react in the lab for a while, maybe a couple of hours before we get a lab product. Once we have this position, now we can do our nitration, because this is meta-directing, which is this position, and our bromine is orthopara-directing. So both groups point towards the position where our NO2 group goes. So based on our directing of NO2, we couldn't add it first, but also because we can't do acylation with NO2. So the order of these are really important. The more you practice, the more you see them. The order that you are reducing or oxidizing is also important based on directing. And you have to consider those two main limitations that we considered, which is acylation and alkylation cannot happen with electron withdrawing groups already present. And this one's not going to come up as much, but you can't add an NO2 if you already have an NH2, because it will react with it. Not enough to say you'll form two NO2s, enough to get a mixture of products that you don't want. So it just causes a mess. Any other routes in this example would give us different directings and different attachments. Now, I'm not going to say that sometimes there will be multiple routes you can take. There will be. But in these cases, these are the only routes that give you the correct directing. So looking at this one, when you're looking at one and it gives you a bunch of lists, the easiest way is to write out the product after each step. Because if you don't do that, you can try to think about it in your head, but writing it out after each step is going to be the easiest. So we're starting with benzene, and we're reacting with our HNO3 and H2SO4, so we're adding our NO2 group. And this is benzene, so we can add at any position. So I'm just going to put it up here for now. This is a double bond. It's just not working for me today. Okay. Now, the next step is adding our BR2. And that's going to add meta to our NO2 group wherever we put it. So that's that position. Just going to put the circle because it's not really being sensitive enough to let me put the double bonds. Now we are reducing it with zinc and HCl. So that will reduce our NO2 to our amine. And our last step, we're adding our SO3H. So our NH2 is a strong activator. And our bromine is a weak deactivator and also orthopara directing. But really our NH2 is going to be strong, so that's going to dominate. So our main is going to be ortho and para. And of course, since NH2 is going to really win. We'll likely have para to the NH2 group based on sterics. While bromine is directing in that ortho position, it's going to be slightly deactivating, so it's not as strong of a director. So we're really just looking at NH2. So breaking it down like that is going to help you when you're looking at ones like that. So that's our electrophilic aromatic substitution. Now let's go on and look at the ring and consider if we react it with a nucleophile. Now we're going to look at nucleophilic aromatic substitution. First off, you need to know the difference between an electrophile and a nucleophile. So let's review. What's our definition of electrophile? Electron loving. That means it loves electrons. So if it loves electrons, what must it have? A positive charge. It must be electron poor. It's electron poor, and it wants electrons. So an electrophile is something like everything we've been looking at that has a pretty strong positive charge, a pretty strong partial positive charge, which is why we reacted with FeO3, things like that, to make it even more of an electrophile. So what's a nucleophile? It's electron rich. Typically, our strong nucleophiles often have negative charges. They have a negative charge. So acting as an electrophile, our ring can act as an electrophile, depending, and we'll talk about what specific conditions we need for the ring to act as an electrophile. So the first thing when you are considering predicting your products that you're going to have to start doing, now that we're talking about reacting the ring with nucleophiles, is look at your reagents on the arrows and determine, does it have a positive charge? Is it an electrophile? Or is it a nucleophile? So if we react the benzene ring with the nucleophile, we can get a nucleophilic aromatic substitution. It is going to have a completely different mechanism from our electrophilic aromatic substitution, and there are going to be a couple of limitations. One, remember our aromatic rings are typically electron rich, so they much better act as nucleophiles. But if we're reacting the ring with a nucleophile, then our ring has to act as an electrophile, so it has to be able to accept electrons. So to do that, we need a leaving group. We didn't have a leaving group in electrophilic aromatic substitution. But for our ring to act as an electrophile, we need a leaving group. So typically a halogen. Notice that in this reaction, our nucleophile OH negative is replacing bromine. In electrophilic aromatic substitution, we never replaced the functional group. We had to have a hydrogen present. But that's not the case in this reaction. Because for the ring to be able to be attacked, we need to have a partial positive charge on that carbon. So we need a electronegative group that can act as a leaving group. So bromine's our leaving group. Also, this reaction won't occur very well unless we have an electron withdrawing group on the ring elsewhere, specifically in the ortho-para positions. And we're going to look at why based on the mechanism. But we need an electron withdrawing group on the ring besides our leaving group. So we want it to be a strong electron withdrawing group. The most common that you're going to see is NO2. Because we have to make the ring electron poor to be able to accept the electrons from the nucleophile. So we need a strong electron withdrawing group and specifically a good leaving group. So we need two things on the ring. We need a strong electron withdrawing group that can make the ring electron poor, and a good leaving group because hydrogen wouldn't be so to do that replacement. So we need a halogen and something else. Also, the last thing that has to happen for nucleophilic aromatic substitution, or we won't get a reaction, is our leaving group must be ortho or para to the electron withdrawing group. So having the strong electron withdrawing group on the ring isn't enough. It has to be ortho or para to the leaving group for the reaction to occur. Under these conditions, 70 degrees Celsius. Now this last step is adding H3O+, but remember, we can't add that H3O+ until the reaction is over because we can't mix a strong base and a strong acid. If we do, then the strong base will just get protonated and won't react. So we can mix them, but then we won't get a reaction. So we must have a 1 and a 2. That H3O+ is just a source of proton at the end of the reaction. So let's look at the mechanism to understand why not only do we need the strong electron withdrawing group, but it must be orthoparent. So the first step, now this isn't a simple SN2 reaction, because SN2 reactions don't occur very well at sp2 carbons, carbon of a double bond. So instead what we'll get is the attack at the carbon where the leaving group is, and that'll push the electrons onto the ring. Now this is going to look similar to your sigma complex, but what's the main difference between this intermediate and the intermediates that we were looking at for electrophilic aromatic substitution? There's a huge difference. What's the difference? What is this intermediate? It's a carbocation. It's not a carbocation, it's a carbanion. Yeah, it's not a carbocation. So for the electrophilic aromatic substitutions, the ring is giving up its electrons and forms a positive charge. So everything we talked about was based on what stabilizes a positive charged carbon. For this reaction, the nucleophile attacks, forming a carbanion. So everything we're discussing has to do with stability of a negatively charged carbon. That stability is opposite than stability of a positively charged carbon. In this case, electron withdrawing groups stabilize a negatively charged carbon, pulls electron density away from the carbon that has too many electrons, therefore helping to stabilize it. So just like our sigma complex, we can look at this resonance structure to understand why we need our electron withdrawing group opposite either ortho or para to our chlorine. And the reason why is, if our electron withdrawing group is ortho or para to our chlorine, then we get this extra stable resonance structure where we get rid of the carbanion. If our NO2 group is in the meta position, we can't ever get this resonance structure, because then the negatively charged carbon will never be directly attached to the nitrogen. So again, this is going to have completely opposite electronic effects than our electrophilic aromatic substitution, because we're talking about a negative charge in the ring, and we're trying to stabilize. So when our electron withdrawing group is meta, we never get this extra stable resonance structure. So that's why our electron withdrawing group has to be orthopara for us to get this extra stable resonance structure. And again, electron withdrawing groups are going to stabilize a negative charge. So we call this the Meitzenheimer complex, which is based on the scientists that first really reported the mechanism of this reaction. Now the last step in the mechanism is going to be reformation of the benzene ring, and that pushes out our leaving group. Now comparatively, we could push out OH, we could push out chlorine. Chlorine's a better leaving group than O negative, so chlorine gets pushed out. It's not about where we're pushing the arrow, it's about what's the better leaving group. Chlorine's a better leaving. So here we are stabilizing the negative charge. Once our chlorine gets pushed out, then we have a stable ring, and the H plus that we put in at the end just neutralizes any leftover sodium hydroxide. We call that working of the reaction. So that's our mechanism, and the key is the mechanism is going through a negative charge. So if we have it in the meta position, we actually don't get a reaction under these conditions, because again, we don't have that extra stable resonance structure. If we use excess NaOH, we may also deprotonate the oxygen. So not only does the H3O plus help to neutralize any of this leftover, but it also reprotonates. So that's just a side thing with the mechanism. Sodium hydroxide can deprotonate the phenol. Without the presence of an electron withdrawing group, at the conditions we've discussed, we won't get a reaction. Unless if we push that to really, really high conditions. And that's going to be the mechanism we're going to talk about on Wednesday to finish up the chapter, which is elimination addition, and is a different mechanism from the one we just looked at. We still need a good leaving group though. So you guys have a good day. I will see you guys on Wednesday unless you're in lab with me. Oh, tomorrow at 3:30. I think. I have a little flyer on the Moodle page. 3 of our students who did undergraduate research programs over the summer, REU programs, are going to be speaking about their experience. Now, they did it in chemistry, but there's REU programs in biology, medicine, psychiatry, psychology. There's REU programs in a lot of fields. It's all the same program. So if y'all are interested, I recommend it. They pay you. They pay for you to go up there, give you a stipend, and then you get undergraduate research, which looks great on your resume. So if you are interested, come to that talk and talk to them about their experiences. The application should be opening up sometime in January, so you can start getting an idea of if you want to do that. They pay you $5,000 to work the whole summer, but they pay for your room and board, so all you have to pay for is meals. So really, you're saving that money the whole summer. It's a good deal, and it looks good on your resume. If you're in my lab, you have to go. But if you're not in my lab, I strongly recommend thinking about coming and talking to those students who've done it. So you guys have a good day.